Patrolling space like a sentry, the satellite telescope SWIFT is on constant lookout for cosmic disasters. And when it finds one, down on Earth, word spreads quickly. Every few days, the satellite spots a violent eruption in deep space, sending dozens of stargazers scrambling. Whether they're seasoned pros or high school amateurs, their goal is the same.
Go to camera focus mode, and then we're going to need to move the dome. Casey?
To catch a glimpse of a star in its final death throes. Going supernova. And leaving in its wake the strangest phenomenon in the cosmos. A black hole.
Nothing survives encounters with black holes. The black hole wins. It wins every time.
When something falls into a black hole, it's essentially gone from our universe.
They rip stuff apart and eat them. And then they burp and they're ready for the next course.
And now, evidence of something even more ominous. A new kind of black hole, of unfathomable size and power.
That's a big galaxy, and right down at the center, we think there's probably a black hole that's got a mass that approaches 1 billion suns.
Today, scientists are finding black holes are bigger, stronger, and more destructive than they ever imagined.
It creates energy fields that would fry any life in its vicinity.
Not only do they consume everything that comes near,
you stick your finger down in there, you ain't getting it back.
But their power may reach across galaxies and beyond.
Did the universe really have to be made with these things in it?
We'd like to think they're far, far away. But what if, in our own cosmic backyard, there lurks the monster of the Milky Way? Right now on Nova.
This is just enormous.
As he pores over a set of x-rays, Brian McNamara struggles to diagnose a complicated ailment.
So that's pretty strange.
But his patient isn't a person or any earthly creature. It's a cluster of galaxies, 2.5 billion light years away, with a giant blast of energy spewing from the center. This is the most powerful explosion in the universe since the Big Bang.
To put this on sort of an Earth scale, it's equivalent to about 1 trillion atomic explosions. So it's an enormous amount of energy.
What could produce such awesome power? Whatever it is, it seems to live at the very core of galaxies. And many believe our own galaxy, the Milky Way, is not immune, harboring a powerful secret at its heart. What could lie at the center of the Milky Way? One of the pioneering explorers of our galaxy is Eric Becklin. He's been trying to unlock the mysteries of the galactic center for more than 40 years. But first, he had to find it.
Back then, people weren't even sure where the center was. There was some vague understanding. There was a radio source called Sagittarius A, a very strong radio source, but there was even debate whether that was really the center or not.
Examining other distant galaxies, astronomers knew that the center is usually the brightest spot, tightly packed with stars. But when they tried to pinpoint the center of our own galaxy, the Milky Way, they ran into a problem. The central stars were shrouded by cosmic dust.
There is so much dust between us and the galactic center, it is completely opaque. You do not see the stars in the galactic center. The most powerful telescopes cannot see it.
But there are other kinds of light that can pass through, like infrared, a form of light and heat invisible to the naked eye that travels in slightly longer waves.
Infrared radiation gets through the dust because its wavelengths are longer and the dust just kind of rides on the infrared wave.
In the 1960s, Becklin belonged to a Caltech team that bought an infrared detector from a military contractor and attached it to the end of a telescope.
It was in August of 1966. I was up at Mount Wilson. It was a beautiful night on a small 24-inch telescope. And as we were looking with the infrared detector, we were seeing more and more stars.
A simple chart recorded the infrared light of stars. Stars that until then had remained hidden behind a veil of dust and debris.
This is the signal in the infrared, and each star gives you more signal. And we were building up, as we were getting closer to the center, more and more stars. We were actually seeing through the dust for the first time, and then came to a peak, and then back down again. And I knew immediately that that was the center of our Milky Way, and that I was the first person to actually see the stars in the very core of our galaxy.
Becklin had located the heart of the Milky Way. From our perspective, an inconspicuous speck near the constellation Sagittarius. The Milky Way is a giant spiraling disk of hundreds of billions of stars, 100,000 light years from end to end. Our sun, about halfway out from the center, sits in the peaceful suburbs. But at the galaxy's core, the neighborhood gets more exciting and dangerous.
There's a lot of gas. There's a lot of dust. This is absolutely the most crowded place in our galaxy.
From Earth, we can see a few thousand stars with the naked eye. If you went to the galactic center, there would be millions of stars filling the sky.
It's the big time. It's where the show really goes on in the galaxy. And so if you go there, you're very much aware of being a tiny little mouse in Times Square, and somebody's liable to step on you.
For years, scientists suspected that a powerful force dominated this galactic Times Square. It had to come from an unimaginably massive object. Some thought it had to be a black hole. An object so strange, it's hard to describe.
What's a black hole? It's a region of space.
It's a point of infinite density. We don't know how to wrap our brains around that. If you fall in, you never come out.
It's not the point of no return, it's the sphere of no return.
Now you throw in a hungry beast in the middle of it all.
It's this monstrous, mysterious thing.
And if you can imagine taking a bowling ball
But, I don't know, eats everything. That's not true.
You have something, you drop it off the top of a building, and you're falling in to the deepest well you can possibly imagine. Physicists have just as hard a time as anybody else understanding this sort of thing.
It's a black hole. There's no other phrase we can possibly use to describe it.
The current idea of this bizarre creature comes from a radical view of space, time, and gravity. Welcome to the universe according to Albert Einstein.
Albert Einstein had this crazy idea that space and time were curved, and it was the curvature of space that gave the appearance of gravity.
We tend to think of space as rigid and stable, But Einstein proposed that space and time are woven together in a flexible fabric. Massive objects like the sun actually bend and warp the fabric of space-time, creating troughs that smaller objects can fall into.
What actually happens is matter warps space-time. So the very space, the three-dimensional space that we walk through, warps slightly. Every time when I walk through space, space around me warps in on me ever so slightly, but because we're not very massive, it's so minuscule that we don't sense it.
If an object is massive enough, like the Earth, it will warp space-time so we can sense it and fall towards it. That's gravity. But what happens if an object is much, much more massive than the Earth or the Sun? In theory, it could warp the fabric so much it would create an actual hole in space-time. Once something fell in, it couldn't escape, not even light itself.
So imagine a place where the gravity is so strong, turning on a flashlight. The light would go up and it would never leave. It would curve and come back down just the way a tossed ball on Earth. It's not traveling fast enough, it goes up, curves, and comes back down.
Space itself is falling inside the black hole. It's rather like a river falling over a waterfall. It's like that, except it's space itself that's falling over the cliff. There's a place where the space starts moving faster than light. So the light, which is trying to get out, it's rather like a kayaker trying to make their way upstream on a river that's going too fast. They get dragged down to the center of the black hole.
Gravity becomes a riptide. The closer you get, the stronger the current. Eventually, you reach the event horizon, the point of no return. Deep inside, whatever goes in is lost in a point of infinite density.
The matter goes inside the surface of the black hole, shrinks down to the very center, where it gets destroyed in a region of infinite warped space and time, and it's gone.
And so, it seems, are the laws of physics. At the center of a black hole, all equations break down. Even for physicists, what happens deep inside a black hole is a mystery.
We're in want of a new idea about how to explain what matter does at the center of a black hole. We're in need of a new law of physics.
Einstein himself concluded black holes were too strange to be real.
Albert never really liked the idea of black holes. He thought they were anathema. This was something that nature should avoid. The places where space and time became infinitely twisted up, he thought, no, nature shouldn't allow that.
Black holes are certainly odd beasts in the universe. They were thought to be peculiar, so peculiar as to perhaps not even really exist in the real world. Simply because your equations show that they can exist doesn't require that the real universe has them.
But over the years, suspicions rose. Stars were found behaving strangely, orbiting invisible objects, moving faster than expected.
Even though a black hole emits no light, is completely invisible, we know exactly what effect a black hole is going to have on its environment, on the stars in its vicinity, on the gas that wanders a little too close. So, will we ever see a black hole? No. But that's not what's important here. What's important here is we can see its paw print.
Suspicious that an enormous black hole was dominating the center of the Milky Way, Eric Becklin was eager to find its paw print. But even with infrared technology, when Becklin pointed the most powerful telescopes on Earth at his target, all he saw was this, just a blur.
The biggest obstacle that we had was the turbulence in our own Earth's atmosphere was blurring the images.
Even when the sky is clear, the gases in Earth's atmosphere are always on the move, distorting distant objects. To bring his view of the galactic center into focus, Becklin would need help. So he appealed to Andrea Ghez, an expert in dealing with the atmospheric blur.
The problems of the Earth's atmosphere is very much like the problem of looking for a penny at the bottom of a river that's moving, where the water is moving by very quickly. That motion of the water distorts your image of the penny. Just like the motion of the air in our atmosphere distorts our images of astronomical objects.
Ghez agreed to take on the quest, to search for signs of a black hole at the center of the Milky Way.
A decade ago, you couldn't look at the center of our galaxy with high resolution, so you couldn't distinguish stars from one another.
Ghez was able to correct the blurring effects of the atmosphere with a revolutionary new technology called adaptive optics.
So this little animation shows you the benefit of adaptive optics. You see the stars without adaptive optics, you turn the adaptive optics on, and all of a sudden you see stars. And in particular, you see stars near the center of the galaxy. Without adaptive optics, you would only see one big blob. And those stars are in fact the most important for us to track. We track all of them, but these are the ones that are the key to the problem. I mean, it doesn't hurt to take more.
Thanks to the new technology, the team could peer into the heart of the Milky Way with amazing precision.
Our view to the center of the galaxy is absolutely superb, and our ability to position stars at the center of the galaxy is like somebody in Los Angeles seeing somebody in New York be able to move their finger like this, okay, just 2 centimeters. That's the precision with which we can measure something that is 26,000 light years away from us. 16 is right there. Here, yeah.
Once the view was clear, Ghez could start the hunt. If there were a black hole at the center of the galaxy, its paw print would be found in the rapid orbits of nearby stars.
Keep our fingers crossed.
The conclusive experiment to be done that really demonstrated there was a black hole is to follow the orbits of individual stars in the galactic center very, very accurately and with the highest precision possible.
When an object like a star approaches another, more massive object, the pull of gravity will make the star speed up. If it's orbiting close to a massive black hole, the star should accelerate to enormous speed and then whip around the black hole like a slingshot.
Okay, so we have the black hole here. The more massive it is, the more pull there is. The more pull there is, as it gets close to the black hole, the faster it goes. And we are measuring the speed of these stars. That's the key to getting the masses, measuring the speed of those stars.
This is our roadmap, and that's the center of our galaxy. There's a large cluster of stars that are orbiting the center of our galaxy, and by measuring the motion of stars, and in particular their orbits, we can figure out whether or not there's a central black hole. That environment in there, it's a crowded party.
Ghez set out to monitor the partygoers, to track every movement of the central stars.
Basically, the way this experiment works is you take an image, you see where all the stars are, and then you come back sometime later and you take another image. And you look to see if they've moved. And so the second time we took an image, we knew we were golden. Those stars had clearly moved. This one moved to here, this one moved to here, this one moved to here, and so on.
As Ghez continued to track the stars, she found some making dramatic hairpin turns.
It made a huge jump to over here. So it went whoop, all the way around. And it's moving on order 10 million miles per hour, so it's just speeding away.
Other astronomers clocked the stars with similar results. Not only were the stars accelerating to phenomenal speeds, their orbits were perfectly smooth. Ghez knew that they had to be circling a single massive object. Most black holes are thought to be about 10 times more massive than our Sun, but the object at the center of the Milky Way was roughly 3 million times as massive. For Ghez and Becklin, that could mean only one thing.
All other physical explanations of what was at the very center were gone. The only thing left was a black hole.
Not only was this black hole supermassive, it was millions of miles wide. Astronomers around the world admitted the evidence was impressive.
I have to say, when I first saw Andrea's video, I was stunned when I saw that star come out of the left side of the frame and go zipping around and go shooting off into the other end of the frame, and it moved around a point in space and nothing was there.
That we could, with our instruments, effectively travel to the center of the galaxy 26,000 light years away and collect the evidence for such an incredible object was really an amazing achievement.
It seemed undeniable. A giant black hole, and at the center of our Milky Way. But how could such a monstrosity come to be? One idea is that black holes are born out of the death throes of enormous stars. Like a red supergiant, a star 10 times more massive than our own sun. Deep inside, temperatures soar above 1 billion degrees. Helium and carbon fuse into heavier elements: oxygen, silicon, sulfur. Eventually, the nuclear reaction creates iron, and the core stops burning. Then, the star implodes under its own immense gravity and goes supernova. What's left is a heavy core of subatomic particles, a neutron star. Only about 10 miles across, but of incredible density.
In fact, it's so dense that a teaspoonful of neutron star matter would weigh about 1 billion tons.
If the neutron star is heavy enough, 3 times more massive than our sun or more, the implosion will continue.
Eventually, the gravitational pressure will be so large that the neutrons themselves will be crushed, and there'll be nothing left to stop the collapse.
The result is a black hole. Many researchers believe that the Milky Way is littered with small black holes, the dark, dense remains of dead stars.
There must be millions and millions of black holes zipping around our galaxy as we speak. But we don't see them in general because they're dead. They're corpses, and there's nothing there to light them up.
They might be invisible, but to a visitor, these small black holes, maybe 10 miles in diameter, would be especially deadly.
One of the scenarios that always gets me thinking is death by black hole.
Approaching a black hole, the gravity is so strong and space is so warped, it distorts the light all around it. If it's a small black hole, then soon you'll be distorted too, by tremendous tidal forces of gravity.
The tidal force is the difference between the gravity at your head and your feet. The gravity at your feet, if they're closer to the black hole, is a little bit stronger than the gravity at your head, and you feel that as something that is tearing you apart.
Stretching you from head to toe. The tidal forces unrelentingly getting stronger as they exceed the molecular forces that bind your flesh. As you snap into 2 pieces, and those 2 pieces snap into another 2 pieces.
And ultimately you will pull your atoms apart. You will be, as we say, spaghettified.
And so you end up moving through space-time like toothpaste through a tube. And if I were to pick a way to go, that's how I'd want to go. It's got to be better than just getting buried. I mean, come on now.
A supermassive black hole, 1 million times wider, might at first seem more inviting. Since it has a larger event horizon, the pull of gravity is more spread out.
If you go to a supermassive black hole, the tidal forces are weak enough that you can fall not only through the event horizon, but deep down into the interior of the black hole.
So, with a good spaceship, you might be able to cross the event horizon into the black hole itself. Now, thanks to a computer simulation based on Einstein's own equations, we can see exactly what such a trip would look like. The supermassive black hole is surrounded by swirling light beams as superheated gas rushes into orbit at high speed. Light and matter are suspended by centrifugal force and then inevitably fall victim to the relentless pull of gravity. At last you cross the event horizon, the point where nothing can escape.
So let's imagine that we fall through the event horizon. That's the place where space is moving faster than light. We fall deeper down inside the black hole.
But don't expect the black hole to be black. Deep within, there's an inner horizon, a logjam of trapped light and energy.
At a certain moment, as we hit the inner horizon, there's this infinitely bright, blinding flash. That's all the stuff that's been waiting there, trying to get out, is just held there at the inner horizon.
Unfortunately, you wouldn't have long to enjoy the view.
It would vaporize you. Roast you, vaporize you, marmalize you. Almost certainly, if you fell into a real black hole, you would simply, unfortunately, die.
Science fiction displays a bit more optimism, like the 1979 movie The Black Hole. Space travelers do indeed fear this massive object.
I will travel where no man has dared to go.
Into the black hole?
Why, that's crazy.
Cuckoo is a Swiss clock.
But even more cuckoo, the heroes actually survive their descent into the beast,
Black hole is pulling us in.
where they're treated to a heavenly experience. Popular culture has cast black holes as the freaks of the universe. And the supermassive black hole at the center of our Milky Way, weighing in at 3 million times the mass of the Sun, seems especially monstrous. But is it unique? To find out, astronomers are probing distant galaxies to see if our giant black hole is one of a kind, or nothing special. The Sloan Digital Sky Survey is taking a census of the big galaxies within 1 billion light years. For every patch of sky, a steel plate is created. Each hole represents an entire galaxy within our view. Fiber optic sensors are plugged in. Each measures the distinctive spectrum of light emanating from a galaxy's core and can detect signs of hot gas swirling into a black hole. You can see the results. Circled in red, virtually every major galaxy bears the signature of a supermassive black hole.
That was pretty amazing. Before that, we thought, yeah, maybe a large number of galaxies have black holes in them, but every galaxy has a black hole? That was something very interesting.
The closer we look to the centers of galaxies, the more we find these black holes, and the inventory is rising high. So any idea for the formation of a galaxy will now have to include some explanation for how you get a black hole in its center.
So how did every big galaxy in the universe end up with a giant black hole in the middle? To understand, we have to go back to the very beginning. The Big Bang.
You got the Big Bang handing you your birth ingredients, your hydrogen, your helium, your traces of some other elements. So it's kind of like this soup. You put it together and stir it.
The main stirrer for the soup is gravity, drawing together wisps of hot primordial gases. Over time, the clouds of hydrogen gas cool down and grow more and more dense, until some coalesce into the first stars. These are giants, hundreds of times bigger than our sun. They burn out quickly and dramatically, in the flash of a supernova. What's left at the core is a black hole.
Perhaps the black hole becomes the seed from which the galaxy sprouts. The gravitational seed that is used as an attractive force to accumulate the rest of what we would today then call the greater galaxy.
Possibly seeded by black holes, the infant galaxies dance and orbit one another as gravity pulls them closer. So our Milky Way galaxy, as this time-lapse simulation shows, was not born in one single event. Instead, it was built over billions of years from a swarm of smaller galaxies smashing together, merging.
But if another galaxy comes too close, they will each feel each other's gravity. And in that collision, what started out as a stately ballet of stellar orbits moving around the center of their galaxy has now become this maelstrom. There's no other way to say it. Galactic cannibalism, that's what they're doing. They're dining on their neighbors, eating entire galaxies. Well, for every galaxy you eat, if that galaxy has a black hole in its center, it's going to eat the black hole. The black hole will work its way down to the center of the large galaxy, making the center of the galaxy bigger as well as the galaxy itself. It's just that simple. The big galaxies get bigger, and the little ones get eaten.
Galactic cannibalism is how galaxies grow, and with them, the black holes at their centers merge and grow bigger. But what does the presence of such a monster mean for the life of a galaxy? Brian McNamara believes he's found the answer, and it isn't pretty.
That's it right there. We got it. That's it. Okay, so you want to go...
McNamara studies the life cycles of the universe's biggest structures, galaxy clusters.
There it is. That's the galaxy. So that's what we've been looking for. This is the giant central galaxy in a galaxy cluster. And each one of these little dots here on the screen is a giant galaxy as big as our Milky Way, maybe even a little bit bigger. And they're all bound together by their own mutual gravity. So they're all buzzing around this giant galaxy like bees buzzing around a hive.
McNamara probes his galaxies with multiple tools. Optical telescopes, radio receivers, even X-rays.
Oh, there we go. Check that out.
X-ray images reveal a vast cloud of hot gas through the whole cluster, across hundreds of thousands of light years.
There's an atmosphere of gas that pervades the entire galaxy cluster, and it's an atmosphere like our atmosphere, except that it's far less dense and it's much, much hotter.
But when McNamara looked at X-rays of the gas around certain clusters, he saw that vast clumps of it appeared to be missing.
I was blown away. I'll never forget the moment we got the observations, and lo and behold, these two giant cavities showed up in the X-ray emission.
The size of the cavities was astounding.
That's 200,000, 600,000 light years from end to end. So between that cavity here and this cavity here, we could stuff 600 Milky Ways in there. It's just astonishing. The energy involved is huge.
Something powerful had pushed the gas away, across vast regions of the universe. McNamara traced the power source to the center of a giant galaxy. A supermassive black hole.
So we could see the beam coming out of the black hole and ending up in these big cavities.
But how can a black hole, a creature famous for devouring everything within its grasp, spew energy across the universe? The answer lies in the way matter falls toward the black hole. It turns out, nothing goes straight in.
As matter falls in, what we know now is that it spirals around in a disk, okay, very much the way when water goes down the drain. It doesn't just go straight down the drain.
Just as water spirals down a drain in a whirlpool, matter and light spiral at high speed into a black hole.
And the speeds that matter can achieve around that black hole approach the speed of light. And when matter travels at that speed, it gets a tremendous amount of energy.
Matter falling into a black hole is a lot of stuff trying to get into a very small place. And so it's like trying to fill a dog dish with a fire hose. Most isn't going to get in.
The black hole chokes on the influx. And the high-speed whirlpool of matter produces a powerful magnetic field, coiling around the black hole and shooting the energy outward. These enormous jets of energy, hundreds of millions of times the power of the sun, can blast right out of the galaxy.
There's no question that the black holes at the centers of galaxies have a profound influence on their surrounding. They send out these huge jets moving at almost the speed of light. And those jets can send shock waves into the surrounding medium and change their surroundings completely. They have a dramatic influence.
Not only can they blast away huge quantities of gas, but they may even sterilize the galaxy so new stars can't form.
The supermassive black holes at the center may be responsible for limiting the size of galaxies. In principle, galaxies can grow to very, very large sizes, and what we see in the universe is that they don't. And we think that the supermassive black holes at the center may be the culprit. They may be responsible for preventing runaway growth of galaxies.
We usually think of black holes as God's dumpster, but they really are actors on the galactic stage.
If supermassive black holes can wreak so much havoc, what's to stop our own monster of the Milky Way from wiping us all out? It all depends on the monster's diet.
Most of the time, a black hole isn't eating. It fasts more than it feasts. But when a black hole feasts, it can have a tremendous effect on the surrounding galaxy.
The more black holes chow down, the more matter and energy will blast outwards.
One of the key differences between galaxies with supermassive black holes is whether or not their black holes are lit up, because they're basically binging on a lot of material in its surroundings.
For years, our black hole seemed to be fasting, and the Milky Way was peaceful. But in 1999, the Chandra Space Telescope detected a powerful signal from the galactic center.
Station 3-4, Chandra OC.
An explosion near the event horizon. Is this the beginning of a black hole binge? For trackers of the galactic center, the blast is a wake-up call.
It was a hot piece of news. A remarkable fact for all of us was, for many years, how inactive the black hole was. And all of a sudden we saw, well, there's an object there which wasn't there before.
Reinhard Genzel has been watching the galactic center for nearly 2 decades. Like Andrea Ghez, he's been tracking the orbits of stars, helping to prove the existence of a black hole at the heart of the Milky Way. Now both Genzel and Ghez will shift their focus and try to measure the black hole's appetite.
One of the big mysteries about the black hole at the center of the galaxy is why don't we see emission from matter falling onto the black hole, or rather the black hole eating up its surroundings.
Genzel and Gez are joining a worldwide effort. Chandra in orbit will take X-ray pictures of the galactic center. At the same time, 5 major observatories on the ground will probe the black hole, all trying to count calories. Genzel heads south to Chile, while Gez and Becklin climb a mountaintop in Hawaii. Telescope time is precious. There's no room for mistakes.
When you're there, it's an incredible rush. I mean, you're very much on for the few nights that you're there, hoping the weather cooperates, hoping that the instrument cooperates.
How's the Act-4 look on the oscilloscope? Does the timing look okay?
Better now.
Okay, let's see if there's something there. Madeline, we're ready to go?
The teams have 5 short nights to find out how much the black hole is eating by measuring the energy that flares out.
Zoom in a little bit more. All right, so first night. Doesn't look like we've got any flares.
Chandra headquarters in Cambridge, Massachusetts. The first night turns up only noise.
4 more chances, guys.
Night 2. Chile has problems.
No, we have to redo the acquisition over.
Even if there are flares, the Chilean telescope can't see them.
It was the correction was
unstable.
Yeah, unstable.
A patch of humidity is confusing the computers. The crucial adaptive optics aren't working, and everything's a blur.
Extremely.
Okay, now we have a problem with the 8 meter, with the main mirror. The 8 meter mirror seems to be deformed.
In Hawaii, it's not much better for Gez and her team. The galactic center is playing hide-and-seek behind overcast skies.
We're fighting with clouds. It looked better just a moment ago, so it looked like we were just ready to go, but now it's looking like yuck.
The Hawaiian forecast predicts even more clouds tomorrow. The team is getting anxious. Finally, on night 3, the German team's luck changes.
They're in correction.
Look at this.
Right.
It's really flaring.
In Chile, they spot an outburst.
That's the best flare event that we saw during this run.
Definitely.
A new point of light appears in the starfield, one that wasn't there before.
Very nice, very nice.
Here we can clearly see a region between those 2 sources where there is no other object. And here we have the same region, the same 2 sources, and now in between we see an additional source. So this is the flaring state of Sagittarius A star.
JPL-COM, Chandra OC.
When the Chandra team downloads their data from space, they see it too.
Oh, yeah.
The X-rays show a spike that coincides with the Germans' flash of light. Genzel checks in with the Hawaiian team, but they're in the wrong time zone.
News from our colleagues, of course, telling us that they are a few hours further west, so the sun hasn't even set yet.
The galactic center hasn't risen above the Hawaiian horizon, and Gez has missed the flare.
This part kills me. Waiting.
But the next night, Gez finally gets what she's looking for.
Well, I like that image a whole lot better.
This is it.
Really?
Yeah. Really.
So in fact, we can see this flaring activity where we think we're seeing matter fall into the black hole. And just a few minutes later, it was absolutely gone.
This now you see it, now you don't flash of light is an explosion of energy produced when matter rushes toward the black hole and some escapes.
We were taking measurements and you didn't see anything from the black hole. All you saw was a star, and then bam, it was there and bright, and 15 minutes later it was gone. So that was our moment to make the measurement, and it was extremely exciting to know that we'd actually been able to catch it.
The teams are thrilled to capture a handful of flares at the heart of the Milky Way, but they're just snacks. Nothing compared to the giant jets seen in distant galaxies. What's more, they're looking like rare events. There's simply not enough matter near our black hole to provide a large continuing feast. It seems, at least for now, the giant's plate is empty.
Our black hole had a wild teenage life. I'm pretty sure of that. It probably had jets. It threw lots of matter out. It had a grand old time. And now it's decayed into the old folks' home.
But what would it take for the monster of the Milky Way to come out of retirement? Could explosive jets of energy blast across our galaxy in the future? Tantalizing clues are turning up in the coldest place on Earth. A Smithsonian team is tuning into high-frequency radio signals from the galactic center. The best reception is at the South Pole. Not as nice as Hawaii, but the date is worth it.
There's some of the gas falling in toward the black hole in the galactic center.
Reading the radio signal, Anthony Stark detects just small amounts of gas feeding the black hole. Nothing too serious. But farther out, about 400 light-years from the galactic center, he can see signs of something much more alarming. A vast ring of matter is gradually growing bigger.
This storage ring then builds up until it coagulates into a single gigantic cloud of about 30 million solar masses.
When the ring reaches a tipping point, it will condense into a giant cloud, triggering a dramatic starburst event, a storm of stars forming and dying quickly. What's left of the gas cloud will spiral down into the grasp of the black hole,
which then rapidly spirals in and feeds the black hole in the galactic center, making the Milky Way an active galaxy.
When the feasting starts, the fireworks will be seen across the Milky Way. But don't bother marking your calendar. Dinner time isn't scheduled for at least 10 million years. The Milky Way will survive its black hole's upcoming feast. But it isn't likely to survive the threat further down the road: galactic cannibalism.
Our galaxy, the Milky Way, is not immune from these colliding galaxy scenarios. We've got neighbors.
2 million light-years away, our closest neighbor, the Andromeda Galaxy, is charging toward us at almost 700,000 miles per hour.
We're falling towards each other, and one day we will collide.
Knowing the galaxy's dimensions and the laws of gravity, scientists can predict how the clash of titans will unfold.
What our simulations show is what could happen basically in quite a few billion years from now, when the two galaxies will actually approach each other and merge.
The merger will take more than 2 billion years, while the galaxies circle and entwine.
Imagine what that might look like from another galaxy. They'll see two grand, beautiful spiral galaxies moving towards each other, slowly losing their shape. They'll see new avenues where stars and gas can funnel down towards this newly formed center, feeding this reborn monster.
The collision will send a blizzard of stars and gas in all directions. Some will shoot toward the crowded core of the new galaxy, spurring massive explosions.
In the process of merging, there will be a very strong starburst event occurring at the time of the merger, as all of the gas is being funneled towards the center.
Amid the turmoil, chances are our little solar system will either witness a spectacular show or be flung out of the galaxy into the voids of space. The Milky Way will be destroyed. But what about the black hole at its center? Most likely, it will merge with Andromeda's, a monster 50 times larger. Stars and galaxies may come and go, but supermassive black holes just get bigger. Once considered freaks of the cosmos, black holes are coming into their own, claiming their place center stage in a violent, changing universe.
As we forge ahead in trying to understand how we came into being and how all of the matter got put down in the universe, we can't leave black holes out of the picture because it seems they play a fundamental role on very, very large scales.
Black holes not only wreak havoc upon the landscape in which they're embedded, they actively shape the landscape. So black holes are kind of the spice of the universe.
Black holes are a major player in the evolution of the things that light up our night sky. They are, in a sense, the secret shadows behind the walls of the galaxy.